of Aristotle's physics, which had these two principles, and then I'll bring up two problems that people noticed about Aristotle's physics, so that in the next video we can go on to Galileo's theory of physics, all of this building up to a theory of physics sophisticated enough to demand calculus in order to solve its problems. So, Aristotle held the very believable principle that forces cause things to change their location or change their displacement. Now, he would never have said it in an equation or in any kind of very mathematically precise way, but he did say essentially this, and he was remarkable for being the first person I know of to have had a completely explicit, precise theory of physics, theory of the motion of objects. And he also held this principle that all things tend toward the center of the earth. And this is what we think of as the gravitational force. And it seems also, another principle is that this force seems to be constant all over the surface of the earth. So that the force that I exert, or that, my phone exerts or whatever, towards the center of the earth is the same here. I could travel to Massachusetts, and the force that I and it exert downwards would all be the same. It would be constant throughout space. I could climb a mountain and I would still be exerting the same force downward. But one of the upshots of this fact that Aristotle seemed to know quite well is that if force is related to the change or the change in displacement, that means it's related to velocity, average velocity. Now, down here I give a mathematical demonstration, a kind of proof that this rearrangement can happen. So the way that I do it is I just work in the delta t quantity. How do I do that? I mean, I can't change this thing, so I multiply by something equivalent to 1, but which allows me to work in the delta t quantity, and then I just kind of rearrange and regroup things. So delta x over 1, you could call delta x over 1 so that you can multiply fractions, and then you group the delta x over delta t, you split off the remaining factor of delta t out to the front. Now that is what we typically call the constant of proportionality, which we don't worry about too much. But it is why I use this funky symbol, which we call proportionate to, which you should just kind of read as directly related. If it's not very familiar what that symbol means, then think that it just says these things are directly related to each other. And so that was Aristotle's theory of physics, but there were some pretty obvious problems with it. For one thing, it provokes the question, why does the same object with the same mass dropped from a small height hit the ground with a lighter force than an object that is dropped from a high position? Because after all, any object will be exerting a constant gravitational force, and therefore it will have a constant velocity. So objects should hit the ground at the same speed, no matter if they're dropped from high or from a short height. But that seems to be empirically false. We can drop things and see the force that they create and know that there's a difference in these forces. So something seems not right about that. Another puzzle is why do objects continue to move even after you've thrown them? So for instance, if you have a ball, let's say, you throw a ball and it goes through some arc of motion. Now you only actually exert a force on that thing up to a certain point, and then you release it, and then it travels, it continues to travel. Why would that be when there's no force being applied to it? I mean, okay, it falls because gravity is pulling it down, or it's exerting gravitational force downward. But why does it continue to move left to right if there's no left to right force being applied? I mean, again, after all, we are talking about taking this idea of force causing your velocity. We're taking that idea very seriously, right? That's the theory, and here it should be predicting that your velocity is zero. Because the force acting leftward is zero in that situation. So that seems like a pretty clear problem. Now, there were some responses to this in Aristotle's time, like Aristotle believed that as the object moved through the air, then air must rush into the vacuum that it leaves as it moves forward, and that rush of air from the back is pushing it forward. Now, that seems like a kind of unsatisfying answer. It seems unlikely that the rush of air behind the ball would really be strong enough to propel it forward, but in any case, these are some problems with Aristotelian physics. One big problem that was historically significant was that a massive object and a light object should fall at different speeds. And for some reason, everybody knew that this was an implication of Aristotelian physics. Even Aristotle understood that this was something that his physics implied, and yet for thousands of years, nobody tested it. It's kind of an amusing fact of the history of science that there was this testable theory that nobody actually measured. Again, the idea being that a massive object exerts a strong gravitational force. It should therefore have a large velocity, and so things that are massive should fall faster. And yet, when Galileo carefully measured this about 2,000 years later, he found that, in fact, objects of different masses dropped from the Leaning Tower of Pisa did not reach the ground at the same time, and so did reach the ground at the same time, and so seem to have the same velocity, contrary to Aristotle's theory. So this all demanded a new theory of physics, especially in the mind of Galileo, who then came up with it, and we'll discuss it in the next video.